catch on, the topic for today is energy. Yeah. And as you guys indicated, energy is the ability to do work. The ability to do work. All right. Few just generic things about energy. Energy is a fundamental property of basically of the universe. It's an amount that cannot be changed. From ninth grade physical science, you guys are probably very familiar with the law of conservation of energy. Law of conservation of energy, what is it?
Cannot be created or destroyed.
Good. Conservation of energy states that energy cannot be created or destroyed. Energy cannot be created or destroyed. It can just change forms. So that was a great definition back in physical science. And we can actually now add a quantitative analysis to that. So what we're really saying is that the sum of the energies at point or time A must be equal to the sum of the energies at time B. Now, in this class, we're going to largely focus on just mechanical energies. We could talk about other types like radiative or electrical or thermal, but largely we're just going to put those aside for now because we'll get to electrical energy in March and we get to radiative energy in April. So we're just going to worry about the mechanical aspects for now. And mechanical energy is any energy that is due to position or motion. So mechanical energies is energy due to position or motion. Now what that means that we see for the law of conservation of energy is really we're going to be talking about the sum of the mechanical energies at point A equals the sum of the mechanical energies at point B. Okay? So in order to actually approach what that means, we need to figure out, well, what are some different types of mechanical energy? Mechanical energies are largely put down into two categories, potential and kinetic. So we'll start with the kinetic energy. Okay? Kinetic energy is the energy of motion. This is how much energy it takes to get something moving at a certain velocity, or the amount of energy that something has once it's reached that velocity, and it maintains that much energy, simply because it can't be created or destroyed. So, the energy of motion. And to determine kinetic energy, we use the equation kinetic energy is equal to 1/2 mass times velocity squared. Taking a look at the units, that means that energy must be measured in kilogram meters per second squared. Okay. Good? Okay. All right. Going forward from there, this is actually a different unit we call a joule. Because saying kilogram meters squared per second squared is a mouthful, we decided to name it a joule. Yes, there was a physicist whose name was Joule. And it doesn't matter what kind of energy we're talking about. We could be talking about kinetic energy, potential energy, electrical energy, radiative energy. It's all measured in joules. And if we talk about even the amount of power in a battery, or amount of energy in a battery, you can look at batteries in terms of the number of amp hours that they've got. Really, that's just a fancy way of saying kilojoules. It's a little bit off from a kilojoule, but um, amp hours is about the same as, I think it's 3,600 joules. So it's just a slightly different version. Okay, so it's all about measuring how much energy something has. We've got kinetic energy. You guys have also encountered kinetic energy when you've talked about heat and kinetic theory of matter back in either chemistry or physical science. And you said that the motion of particles or temperature was a measure of their average kinetic energy. Well, now we can see that depending on the mass of the object, the speed would be slightly different for a set kinetic energy. How many of you remember the kinetic theory of matter from chemistry? Yes, a little bit. So one of the parts would have been that at a set temperature, particles of greater mass move at a slower velocity, slower average velocity. Well, that's because of how kinetic energy is calculated. As you increase the mass of an object, the velocity has to come down to maintain the same kinetic energy, or for a particle, that means maintain the same temperature. Good? All right. So, big detail here, I want to point out that velocity is significantly more important to determining the kinetic energy than mass is, as illustrated by the fact that it's squared. Okay? All right. Moving on from kinetic energy, we have potential. The two types of potential energy we're going to talk about are elastic and gravitational. There are other types, but we'll get to them at other points in the year when we're not talking about mechanical energy. So it's just energy due to position. To position. In terms of gravity, gravitational potential energy that's the energy something has due to its capacity to fall. Energy due to a capacity to fall. Now, calculationally, that can be found as GPE equals mass times gravity times height. Alternatively, you could call that force of gravity times height, because we know that mass times gravity is the force due to gravity. Okay. Looking at our units, we've got kilograms, meters per second squared, and meters. Hey, look, what's that the same as? A joule. Okay. And next up, lastly, we've got elastic potential energy. Which is the energy present in the presence of a restoring force, or energy caused by the presence of a restoring force. Energy caused by the presence of a restoring force. Now, this could be something like a spring. It could be something like a coiled rope. It could be something like a rubber band that's been stretched. Anything that's trying to exert a force to bring it back to a relaxed position is a source of elastic potential energy. So a slingshot, a wrist rocket would have elastic potential energy. A coiled rope ballista would have some elastic potential energy. Yeah, Admir.
Doesn't like everything technically have it just extremely low?
No, not necessarily.
It's like you could take like a box or something and pull it, and it would slightly like move.
Well, like stack of paper currently has none. if I close it, sure, it's got some force trying to push it back. We could approximate it as a spring and call it a restoring force. Yeah, we could do that, but like as it's sitting here now, if I'm pushing it together closed so the pages are compressed, sure, yeah, we can approximate that as a spring. Okay, springs and rubber bands are typically the ones we talk about for elastic potential energy. And we can calculate elastic potential energy, EPE, as being equal to 1/2 kx squared, where k is a spring constant that is dependent upon the individual spring or source of restoring force. Depends on the specific source of restoring force. And x is the displacement that you have either compressed or stretched your spring from its relaxed position. Displacement from relaxed position. All right, so since we know that energy is a joule, and joules are kilogram meters squared per second squared, and x must be a displacement, so that's meters squared, that means that k, the spring constant, has to be a kilogram per second squared. So spring constants, or k, are measured in kilograms per second squared. Well, that's kind of weird. That's actually not very common. The most common way to write spring constants is rather than kilogram per second squared, because that's really abstract. Most common way to write it is newtons per meter. So that we have the amount of force per meter that something is being stretched or compressed. Spring constant units. So really, either of these would be acceptable. This is really weird. This is less weird because it makes a little bit more fundamental sense. Okay. All right. So we kind of just crashed through 3 different types of energy, a category of energy, and a law. Questions on any of those individual pieces? Yeah. Absolutely. Yep. We can even manufacture a couple of different springs that'll be roughly the same in constant, but if you stretch one out too much and it doesn't go back to its original position, it now has a new K value. So yeah, it's very specific to the materials you're working with. Good? Yeah. Okay.
How do you get newtons per meter from kilograms per second?
Sure. So really what we did in each case was just multiply it by meters over meters. Kilogram per second squared times meters per meter. So that would be 1, right? And I'm just going to rearrange this a little bit. Kilogram meter per second squared meter. Times 1 over meters. Agree with me that that's still the same mathematically? Well, that's a newton. So that must mean that this is the same as newtons times 1 over meters, or newtons per meter. So conceptually, it's the same, and it makes a little bit more sense to say it that way. And mathematically, we just multiply by 1 effectively. Good? Other questions? Okay, so demonstration then. The effect of the bigger the riders you've got, the more energy you've got. Well, the bigger the riders you've got, the more energy you need, because it's hard to get heavier objects, more massive objects to go at a higher velocity. So if I just divide out m then I get GH equals half V squared at B at A equals GH at C plus half the velocity at C squared. What happened to my mass? It's gone. The mass of an object does not determine its ride on a roller coaster. So it doesn't matter what the size of the people in the roller coaster are, you're going to get the same ride every time, which is why the roller coaster operators don't need to be physicists in order to figure out who can go in the roller coaster to make it a safe ride, because the mass doesn't matter. It cancels out in each situation. So if we have a bigger bunch of riders, they have more energy, well, they need more energy, otherwise they won't go as fast. If we have little riders, they don't have as much energy, well, they don't need as much energy. And regardless of who's in the roller coaster, you will always get the exact same ride every time. Yeah.
But like, wouldn't like bigger riders have more potential energy?
They do.
So then like,
And they go the same speed because they needed more energy to get to that speed.
yeah.
Where can I push them out or to go faster?
All right, so there's the important question.
You would do it right at the bottom.
You would do it right here at the bottom. So you've got the most amount of gravitational potential energy at the top, right? So the reason you push them out, well, actually, let me think about it. No, won't work. Because you've got your gravitational potential energy at the top, right? Well, we could break that into gravitational potential energy of rider A plus the gravitational potential energy of rider B. Okay? So we've got those two different sets. That means mgh plus mgh. Let's go 1 and 2. I've already got A and B in this situation. Well, we get down to the bottom. We get down to the bottom and we've got half m1v squared plus half m2v squared. All right, and now Andrew pushes guy number 1 out of the car. Well, he keeps his kinetic energy because he keeps his mass. So that means that that much kinetic energy just came down here to point D and kept moving forward. And now you've only got this much kinetic energy. Well, you'll go back up to the top with that same amount of energy. So what you need to do is somehow get him to give him his energy and give you his energy and take away his mass, which, yeah, I got nothing. So you can't actually push him out at any point because he takes his energy with him because he takes his inertia with him.
But like, wouldn't his inertia cause the car to go faster? So then, therefore, when he
Well, you can't separate his energy from his mass. Yes. And the reason that it needs to is if you think about it in terms of some of those hills where it just barely reaches the top. If it went a little bit slower just once, it'd go backwards and you wouldn't get to the top of the hill. Or on some of the ones where you get going and what if it goes a little bit too fast one time? It could be a bad experience. So precision engineered roller coasters are designed in such a way that, and it really doesn't matter what roller coaster we're talking about, it can be an aluminum one, it can be a wooden one, they're all designed with energy in mind, and it doesn't matter what you do with the mass. You can have any massive rider. All that matters is that the rest of the trusses underneath here be able to hold them.
So would heavier people cause more wear on the roller coaster?
Would heavier people cause more wear on the roller coaster?
They have more gravitation.
Oh, yeah, that's true. That I'm not 100% certain on. It seems like it would, but I think that the mass of the roller coaster cars themselves are so much greater than any rider that you could put in them that it doesn't matter. Yeah. All right. Questions on how the mathematical representation applies to a situation like a roller coaster? what I'd like you to do is take our example here, and I want you to tell me how fast you're going at point B and point C. Take the example that we've got here. Tell me how fast you're going at point B and point C. Is a scalar unit. Okay? So that means that if I take a look at a couple of different roller coaster designs, that one, we'll say this goes from a height of 30 meters. And let's say I've also got that one. Okay? So, and this is also going from a height of 30 meters. I want to know when you reach this point at zero, which one will you be moving slower on? Which location would you be moving slower on for different roller coasters? What do you mean neither?
Because the energy is the same for both, because the initial energy, the initial joules that you start with is the same.
Okay, so because they've got the initial amount of energy put in, then they need the same amount of energy at the end. And they'd be the same. Brennan?
Because the loop-de-loops are assuming the same height, so you gain and lose the same amount of energy.
All right, so they're still working with the same total energy, even though you're doing some loops. Yeah?
Are you using like friction?
There's a good question. Okay, so this has two answers. First answer, if we decide to not look at friction, Nathan's answer is right. They would have the exact same speed at the end. However, when we turn on friction, now we're starting to talk about the thermal energy that comes out of the system. Thermal energy, in terms of this class, we will talk about as work. Okay? Work. Wait a minute. We've heard work today. Where was it? Okay, what was energy? Great, what's work? You're going to love this definition.
Move it up.
The ability to do anything.
Make use of energy.
That's most.
So we need a better definition because that's awful. Okay, so work is the transformation of energy from one type to another through the application of a force. The transformation of energy still kind of circular from one kind to another. Through the application of force. Okay. Mathematically, work is calculated as work is equal to force times displacement. Okay. This is also measured in joules. And if we wanted to then talk about our roller coaster scenario, we could talk about friction in this case. So the work due to friction would be equal to the force of friction applied over the course of the track times really the length of track that we ride. Because it's worth noting, we turned on friction. Now, how do I increase or decrease the force of friction? location, or material, notably not mass. Because if I added this into my equation, really what I could be talking about would be mu times force gravity times the, I believe it's cosine of some angle. No, you'd be able to work it out. But what I'm going to point out here is, how do I figure out force gravity? Mass times gravity. So if I went and took our equation here and added in work, is mass going to matter? No, because it's going to be divided out. And I can divide it out. So even when we do consider friction, even when we turn friction on the roller coasters, mass still doesn't matter because it still cancels out.